Hello and welcome to this applications video on refraction, in which we're going to explore some of the cool features that result from this sort of refraction interaction that we discussed in a previous video. Okay, which is nicely summarized here, that when you are moving from medium 1 going into medium 2, you can write down that your index of refraction in the first medium is the sine of the angle with which you're moving with respect to normal at that in that first medium, and that's going to be equal to just the index of refraction in the second medium times the angle, sine of the angle with which you're moving in that second medium. So refraction can result in quite a few things. One of them is this idea of dispersion, basically creating rainbows. And the reason for dispersion is that although we've written this nicely and it's true, the index of refraction of a material actually changes for different wavelengths of light. So if you make n here depend on the wavelength, then what you can see is if I send in light that has many different wavelengths in it, which is most real light actually is a mix of different wavelengths of different colors, as I do that, well, I'm going to apply this for each particular index of refraction at each wavelength. I'm going to be getting different angles out. Theta incident should presumably be the same. We've emitted it and it's all moving to this boundary, but the moment it hits the boundary, it is going to do this sort of refraction with different values of n for each wavelength. And what that means is I'm going to get different angles for each wavelength. So I'm going to take this light, which was comprised of several wavelengths, and I'm going to split them out. Instead of having one ray coming in with all those different wavelengths, I will get each wavelength going to a different location. And that is what happens with rainbows. They interact with the water droplets, they get refracted in different ways, and the light spreads out. The light from the sun is actually comprised of the entire visible spectrum and then some. And that visible spectrum, instead of being one single ray, now gets spread out. Now, a slightly more technologically useful approach, although dispersion is also useful if you want to do things like figure out what different wavelengths are present in your sample. Total internal reflection is useful for something like fiber optic cables. Now, total internal reflection just says, look at this equation, and imagine that if you make N2 lower, well, you know that you're bending away from the normal. As we talked about in the introduction to refraction, higher indices of refraction bend you toward the normal, and lower ones bend you away from the normal. So as I've drawn it here, you can see this one is bending away from the normal. But what happens if I make N2 sufficiently small that this angle wants to swing all the way out and even maybe continue on back that way? Can I do that? So there is this idea of what if we're sort of bending too far. So it turns out that if you use, for instance, this particular value of the angle, well, let's see what happens. If I put in that this is theta 1 is the arc sine of n2 on n1, then when I take the sine of the arc sine, I'm just going to get n2 on n1 back. And so I will be looking at this sort of equation now. And then if I cancel my n1s and I cancel my n2s, what am I looking at? I'm looking at 1 is equal to the sine of theta 2. And what does that mean? It means that theta 2 has to be pi on 2. It has to be 90 degrees. So if it has to be 90 degrees, well, then I have indeed bent too far, because now I'm running along this edge. All right, what if I tweak theta 1 a little bit more? Well, if I make it even higher, I would want to come out of the medium. So you instead get this total internal reflection, which says that as I'm wanting to go from this medium into that medium and do this crazy excessive bending, I instead reflect. And then I reflect in the normal way, so that this would be my theta out, which is equal to my theta in. And I got my normal reflection happening. And this is useful because then you're saying that at this interface, I haven't lost any of the light. It has now all reflected because the refraction was not possible. And this is what fiber optic cables do to basically try to losslessly send a signal over great distances.